Okay, so right in the middle of our conversation of a discussion of IR signals, right? And we said that there were three characteristics of IR signals. The first characteristic was wave number, that is, where does the signal show up on the spectrum itself? And let's go with green. And we said that the wave number is affected by the mass of the atoms that make up the bond, as well as, what was the other thing? Oh, the bond strength, right? The bond strength, right? Those two things affected the wave number. And the second thing we talked about was the intensity. And the things that affected this was polarity, right? And the number of bonds detected. For example, if there was a lot of CH bonds, then that would make the CH peak even more intense, right? Well, the third characteristic we're going to consider is shape. Now, remember, by shape we mean that some peaks are really broad and some are not so broad. So the question is, why, for example, would the OH stretching be so broad? Well, the reason it's broad is because there are transient hydrogen bonds that are happening all the time in alcohol solutions, right? I shouldn't say all the time. I should say it's very common, but they're transient. They're very short-lived. So if there were no hydrogen bonds, if this did not exist, then this would not be a broad bond. This would have a very characteristic wave number. However, since these guys are floating along in solution, and every once in a while, if actually rather frequently, there will be another electronegative element which makes this transient interaction, and that weakens this bond. Now, if you have, that's why it's broad, because some populations, like a Gaussian curve, some population is always in some stage of having that hydrogen bond. If it's in full-fledged, this is going to be a much weaker bond, and it's going to be further upfield. If it's all by itself, it's going to be further downfield, and that's why we get the broadening of the NH. It's because of hydrogen bonding. So yeah, here's an example of that. Here's where you get, these guys are participating in hydrogen bonding, and here's some OH which is not participating at all. It's just out here by itself. Okay? Now we're not always going to see that. For example, if we have a carboxylic acid, and recall that a carboxylic acid looks like this, right? If we have a carboxylic acid, then we don't have necessarily that free OH down here, but this goes even further downfield. So with an alcohol, remember we saw that big curve here at 3400. Right? Let's get rid of that. But it's further upfield. And why is that? It's further upfield. Oh, by the way, here's that characteristic. Look, 1700. There's the CO double bond characteristic, right? Love it. So why is this so broad, and why is it so far upfield? Well, it's because carboxylic acids are capable of dimerizing. That is, that they can make some kind of a less transient hydrogen bond. It's a much longer-lived hydrogen bond, and therefore it brings the whole population upfield a little bit closer to 3,000. All right, can you see the hydrogen bonds here? Right, you see what's going on? This is a bit of a busy structure, right? But you got your partial negative, partial positive, partial negative, and then this guy goes, hey, there's a hydrogen bond right there. And since he's so close, this other one, it's like a tether. It's like they're chained together. It's like a cage fight between these two guys, right? So then we got this plus and this minus over here, and they go, hey, while those guys are dancing, we might as well dance, right? And so this is much less transient of a hydrogen bonds, and so consequently it's going to bring the whole peak upfield. Okay, so now NHs, which are, as you know, for amines, are also capable of hydrogen bonding, right? There's ammonia, okay? And so if you have another ammonia in solution, or another nitrogen, right? Let's go with a different color. There's a nice hydrogen bond right there, right? So since they're also capable of hydrogen bonding, they also, their peaks are also broadened some. Now this is interesting and telltale. Primary amines often exhibit two signals for the NH bonds, and secondary amines exhibit only one signal, and let me show you what I mean by that, and then I'll show you why. So if you've got two hydrogens, that's a primary amine, right? And here's a secondary, because there's only one carbon there, right? And here's a secondary amine, it's got two carbons on it. This has got two separate peaks, and this one only has one because it only has this one, okay? And here's the reason why. It turns out that the stretching that's observed by IR spectroscopy is actually two different kinds. One is symmetric stretching, and then there's asymmetric stretching. And that is symmetric is where these guys are both going at the same time. They're both going toward the nucleus at the same time, back and forth, right? And it's symmetric. But asymmetric stretching is where one's going in and the other one's going out. And it turns around at any point in time, half the molecules are stretching one way and the other half are stretching the other way. And so that's why we've got two different kinds of signals for, that would be a primary amine. All right, so in review, we have the shape of the signal is important. This is sort of a weird shape. It's like, a double tooth, right? But mostly the shape we focused on was the broadening, and we also focused on the bringing this upfield. It's really sort of the wave number issue, right? Bringing this upfield, but this was because of hydrogen bonding.